In our next section with redistribution, we're going to look at an example of a loop that would occur based on the metric value and the different ways that we can prevent this based on route tagging or filtering with access lists, prefix lists, and with administrative distance. Now, the previous problem that we looked at was related to EdgeRP's behavior, where a route that is not installed from the topology into the routing table cannot be advertised by the protocol. With the previous topology, we would have also seen the same case if EdgeRP had been replaced with RIP, because likewise, if RIP does not install a route into the routing table, it means that it cannot advertise it. Now, in either of those cases, usually they're based on administrative distance-based loops that can only be solved by changing the distance. Now, in this topology, we have a different case where there are multiple points of redistribution between the RIP domain and the OSPF domain. Now, as I mentioned before, in a topology like this, if there were only one single point of redistribution, so if router 3 did not exist in this network, then we would never have a case for a possibility of a loop. We could simply go to router 4, redistribute OSPF into RIP, redistribute RIP back into OSPF, and we would never have a problem. The issues with redistribution are going to come into the topologies when the protocol is meeting multiple times. Just like the case where we had before, where OSPF and EdgeRP were running on multiple routers at the same time, then we would have a potential issue with routes learned from both EdgeRP and from OSPF at the same time. So the case is going to be similar in this example, but the loop here is going to be based on wrong metric values, not on the wrong administrative distance. So ultimately, router 6 is learning routes from BB1 via RIP. These are then being advertised out all its connected interfaces. These are going to router 4, to switch 1. From switch 1, it then goes down to switch 3 and over to router 3. Router 4 is then going to be redistributing these prefixes into OSPF. From router 4, they go to 5. From 5, they go down to switch 2 and switch 4. From 5, it then goes back to router 3 and back to router 2. Then there would be additional LSA flooding on the link between router 2 and router 3, but based on the default costs, we should see that most likely that link is not going to be used. Now, with just the single redistribution on router 4, what is the potential problem that we now have between the RIP and the OSPF domains? We see that on router 3, we now have multiple potential paths to the same destination. One of them is going to be coming from RIP with a distance of 120. One of them is coming from OSPF with a distance of 110. So this means for prefixes that are the same longest match, router 3 would be installing the OSPF route over the RIP route. Now, in this topology, it really doesn't matter which way router 3 installs the route, as long as we ultimately have reachability to the destination. What would be a problem in this type of topology, though, is that if router 3 had a link to some other device in RIP, let's say router 7, and this link was running RIP, when router 3 chooses to install the OSPF route over the RIP route, what would this then imply about advertisements from router 3 to router 7? For any RIP prefixes that are not installed in the routing table as RIP, those would not be advertised out that link. So if router 4 is the only one doing redistribution of RIP into OSPF, it essentially means that router 7 would be isolated from the rest of the RIP topology. So again, there's really no general rules that you can apply onto redistribution. You simply need to look at the flow of the topology, look at where the routes are going to be advertised on a hop-by-hop basis, and that's going to give you a better idea if there are potential problems in that individual topology design. So here our problem is unrelated to that. We have, again, the routes coming from BB1. These are advertised everywhere into RIP. Router 4 is doing redistribution of RIP into OSPF. The routes get to 5. 5 should send these to switch 2 and 4. 5 sends them back to 2 and 3. Now router 3 has the route through OSPF with a distance of 110, the route from RIP with a distance of 120. This then means that the RIP route is no longer installed in the routing table, and the OSPF route takes its place. Let's also now say that router 3 is redistributing from OSPF back into RIP. Now, depending on what the seed metric is that router 3 configures, when 3 sends this to switch 1 now has 2 possible choices. Both of these are RIP routes with a distance of 120. So this means that we would then need to look at the metric or the hop count. So whichever hop count is lower, that would be the route that switch 1 installs into the routing table, which means that is the one that it continues to advertise. So what could be the potential design problem in a topology like this? If we're doing mutual redistribution on both router 3 and router 4 at the same time between OSPF and RIP. Now let's look at it from the perspective of just one individual prefix. Let's say that BB1 is advertising to router 6 some prefix X. At this point, router 6 has X via BB1 from RIP. 6 then advertises this to router 4. Router 4 says I have X via RIP via router 6. 4 is then redistributing this into OSPF. Goes from 4 to 5. 5 says I have X via OSPF via router 4. 5 sends this to 3. 3 says X is via OSPF from router 5. Now router 3 is doing redistribution of the same prefix back into RIP. Switch 1 now has multiple paths to the same destination. It has X via RIP in both cases, but one is via router 6, one is via router 3. So it's going to pick whichever one of these has the lower hop count. So really it depends. When I learned these routes originally in from BB1, what was the metric that router 6 was receiving? Let's say theoretically the metric is 5. When router 6 receives the metric of 5, it's going to increment this as it's advertised out to switch 1. Switch 1 now says I have it as a metric of 6 if I were to go through router 6. Then the metric via router 3 is going to be dependent on what we set the seed metric as. Let's say we set it to a metric of 1. This would then mean that switch 1 invalidates the update coming in from router 6 and prefers the update coming in from router 3. Now at this point, that's not necessarily bad. It's just most likely suboptimal routing to get to the destination. It basically would mean that switch 1 would route its packets this direction in order to get to BB1. But now what's going to happen if switch 1 advertises this route up to router 6 with a metric of 2? Router 6 now says I have 2 possible paths to the destination. One of them is via BB1 with a metric of 5. One of them is via switch 1 with a metric of 2. Since they both have an equal administrative distance, then we're going to look at the metric value. Metric of 2 is better than a metric of 5, which means that we install the route via switch 1. We withdraw this route. Then we advertise to router 4 the route via switch 1. Now, whether this problem is actually going to happen is dependent on what the underlying metric values are. If it just so happens that the metric value from BB1 is already lower than the metric that router 3 is seeding, we wouldn't see the problem. The issue is that it's non-deterministic. It depends on the different variables in the topology that may or may not be within our control. So in reality, to fix this problem, we wouldn't want to change the metric value. What we would instead want to do is tell router 3, when a route goes from RIP to OSPF, then I'm going to redistribute OSPF into RIP. Don't redistribute the routes that router 4 already learned from RIP. So if we were to put these into two categories, if we said that the routes that router 4 learns from RIP, we'll say that these are R4, and the routes that router 4 is learning from OSPF are O4. When router 3 does its redistribution from OSPF into RIP, basically we should say don't redistribute those RIP routes from 4. But we could redistribute anything that's actually learned from OSPF to begin with. So we'll see implementation-wise, there's a number of different ways that we could do this. One way would be to match on the exact prefixes. So I could say match all the individual routes that are inside the RIP domain, then on router 3 tell it not to redistribute these from OSPF into RIP. I could also match on the route type. I could say on router 4, when I redistribute from RIP into OSPF, I'm going to set these to external type 1. Then on router 3, when I go from OSPF back into RIP, I could say not external type 1 routes, and then permit anything else after that. It would mean these particular prefixes would not be redistributed again on router 3. Okay, another method would be to use the route tag that is included in the OSPF and EIGRP update. On router 4, as we redistribute routes from RIP into OSPF, we could set a tag value of any arbitrary number that we define. Let's say we'll set the tag value to be 4. When router 3 now redistributes from OSPF into RIP, we would say redistribute not tag 4, but then anything else after that. So this type of implementation would then automatically account for any new routes that were injected into the RIP domain. So it really is a design question as to, do we want absolute control over what particular routes are advertised, or do we just want to put them into a more general category? If we wanted absolute control, then we would have to actually match the prefix with a prefix list or an access list. But if we're looking at just a general category, we're saying on router 3, don't redistribute anything that router 4 already did. This is generally what the tag value is going to be used for. There's a question here. As I said earlier, it's nearly impossible to have a routing loop if you redistribute only on one router. How would a loop occur? Well, the loop is only going to happen in this place if we do redistribution on multiple routers. So if I don't do any redistribution on router 3, it's not going to be an issue. Okay, the key is you need to look at a topology where the same routing domains are meeting in multiple places. So in this case, we have the RIP domain, where we could say that this is routing domain A, and OSPF is routing domain B. A and B are meeting at router 4, which is fine. It's not necessarily going to cause a problem. But now A and B are also meeting again on router 3. This is then a potential issue that we need to watch out for. Because anything that comes from A to B could potentially be fed back from B to A, and then we could either cause a loop based on administrative distance or based on the metric value. But if router 3 did not exist in this topology, if the only meeting point between these protocols was on router 4, then we don't need to worry about any type of filtering. So we don't need access lists or prefix lists or route tags or administrative distance. We could simply go under the RIP process, say redistribute OSPF1 metric 1. Then under OSPF, say redistribute RIP subnets. It's only the case where there's multiple meeting points between the same routing domains. Okay, it could also be a case where there's a third protocol that's meeting, which will be one of the examples we'll look at after this. So if we had, for example, OSPF that is redistributing into EIGRP, then EIGRP is redistributing into RIP, and RIP is redistributing back into OSPF, this is the same type of case. Because there's now nothing preventing a route that came from OSPF to begin with to go to EIGRP, from EIGRP to RIP, and then get redistributed back into OSPF, and then is starting to route the traffic that way. But if there were only two domains to begin with, if there was only EIGRP and OSPF, then we could never have this problem. Then likewise, if there's a second meeting point between them, this is again a potential issue. Because we don't want the prefix A to go from OSPF to EIGRP and then get fed back into OSPF. This is the case where what we're going to look at here. So let's actually look at this on the command line. At this point, if we look at the routing process on the devices, the meeting points, which are router 3 and router 4, up to this point, we're not doing any redistribution. So on router 3, if we look at the show IP route RIP, we see we have prefixes that are coming from the RIP domain. These 212 routes, these are the ones that came from the external BB1 router. So router 6 is learning those from BB1. 6 is then advertising them to switch 1. Switch 1's advertising them to router 3. Likewise, router 6 should be advertising these to router 4. So at this point, we should have reachability to these prefixes because they're internal to our routing domain. Router 3 is able to reach them, and then likewise, router 4 should be able to reach them. Okay, the next step, we're going to redistribute from RIP into OSPF, and then from OSPF into RIP on router 4. So first, let's go under the OSPF process. We'll say redistribute RIP subnets. Under RIP, we'll redistribute OSPF1 and give it a metric. We'll say metric 1. Now on router 4, we could verify locally, did this redistribution actually occur? So if we show IP RIP database, we should see the routes locally getting redistributed, which they are. If we look at the OSPF database, we should see type 5 external LSAs that are generated by router 4, which they are. So this is telling us now bidirectionally redistribution from RIP to OSPF and from OSPF to RIP is working. So now let's try testing the reachability. Let's say we're to go to switch 2 and we want to test reachability to these different RIP routes. So again, we could do these all individually, or we could do these with a TCL script. So the vast majority of these prefixes are the same as our previous example, with a few minor differences. Okay, the external routes that I now want to test are 212.18.0.1, 212.18.11, 2.1, and 3.1. The rest of the routes are internal to the rest of the topology. And also router 1 is not part of this. So I'm going to remove any of the links that are referencing router 1 here. So from switch 2, we should see that pretty much everything we have reachability to, which we do. So this is telling us that since there's only a single point of redistribution, there's no need for us to do any filtering. There's never going to be a case where router 4 redistributes from RIP to OSPF, then the route comes back in a different interface, and router 4 redistributes from OSPF back into RIP. Why would this case never occur here? Because remember, OSPF doesn't use split horizon, so we are going to run into a case where router 5 advertises router 4's route back to itself. When router 4 originates the RIP route into OSPF to begin with, what is it using for loop prevention? It's using its OSPF router ID. So inside the type 5 LSA, if we were to go to router 4 and say show IP OSPF database for the external route 212.18.00, router 4 says that the advertising router is 150.28.4.4, which is the same as our router ID. So it says we are the originator. This means that if we were to learn this LSA in a different interface, router 4 would automatically discard it. The same case would be true if this were EIGRP. Since both EIGRP and OSPF use the router ID as essentially a tag value inside the external route, there's never a case where we would go from RIP to OSPF and then send the same route from OSPF back into RIP, assuming it's only happening on one router. The problem that we're now going to need to prevent is that it's happening on multiple routers. There's now nothing stopping router 4 from sending the routes to OSPF. They arrive at router 3, then 3 to advertise them back into RIP. So if we look at router 3 and look at the show IP route, we should now see that those routes that were previously installed as RIP are now being installed as OSPF, because the distance of OSPF at 110 is lower than the distance of RIP at 120. So now let's do the same type of redistribution on router 3 without doing any filtering, and then we'll look at what the end result is. So on router 3, let's go under the OSPF process. We'll say redistribute RIP subnets. Then under the RIP process, we'll say redistribute OSPF 1. We'll give it a metric value of 1. Now, if we look in the OSPF database, show IP OSPF database, and I want to know what are the LSAs that router 3 is locally generating here, the type 5AS external link states. It says I'm originating 150.28.4.0 and 155.28.37.0. So only 2 prefixes there. Why would router 3 now only be redistributing 2 routes from RIP to OSPF and not everything that came from RIP to begin with? So let's take this 155.28.9.0 as an example. That is the prefix that switch 3 has assigned on that VLAN 9. From switch 3, this goes to switch 1. Switch 1 sends it to router 3. Switch 1 sends it to 6. 6 sends it to router 4. 4 is now redistributing from RIP to OSPF. Eventually this gets back to router 3. 3 now has 2 routes to the destination. One of them is the OSPF route with a distance of 110. One of them is the RIP route with a distance of 120. What is this now going to change on router 3? Well, we know that the OSPF route is going to get installed in the routing table, right? Because it's the one that has the lower distance. But what else is that going to affect about the RIP domain now? If the RIP route is not in the routing table, it also means that it cannot be redistributed. So we end up in a case here where even though router 3 is doing RIP to OSPF redistribution, nothing is being originated with the exception of that connected interface. And there was one other route that we saw. It was I believe the loopback of router 4. And I believe the reason why this is being advertised, if we look at the show IP route RIP versus the show IP route OSPF, this particular prefix, this is the loopback address of router 4, whereas in OSPF, this is being learned as a host route. Because by default in OSPF, the loopback is treated as network type loopback. So from router 4's perspective, this route is advertised, the loopback of router 4 is advertised into RIP as 150.28.4.0/24. Into OSPF, it's advertised as 150.28.4.4/32. So it's simply that there are 2 different routes. One of them exists only in a RIP, and one of them exists only in OSPF. Now, I could fix this if I went to router 4 and said on the loopback, IP OSPF network point-to-point. This should then withdraw my /32 from the OSPF domain, and it's going to replace it with a /24. So now on router 3, when we look at the show IP route RIP, basically it has nothing here. If we look at the OSPF database, we should now see the only thing that router 3 is redistributing is the connected interface that's running the RIP process. So this is a key point to note here because, again, the redistribution happens from the routing table, not from the routing database. The end result of this is going to be that essentially whoever performs the redistribution first is going to be the device that is preferred for the OSPF route. So let's say we were to go to router 3 and we do a trace route for that particular prefix. If router 3 is using the RIP route, then the traffic should go that way. If it's using the OSPF route, then it's going to go this way. So on router 3, let's trace 155.28.9.9. Now we have a problem. So we can see in the trace route from router 3, the packet goes to 5. From 5 it goes to 4. 4 is sending it to 6. 6 is sending it to switch 1. Then switch 1 sends it back to router 3. So where really we want the traffic flow either to go that way or to go this way, as long as we end up at the destination, which is v.9. But now the problem is the traffic goes from router 3 to 5, 5 to 4, 4 to 6, 6 to switch 1 back to router 3. This now means from switch 1's perspective, it's the one making the incorrect routing decision. It's sending the packets to router 3, where in reality it should be sending them this direction down towards switch 3. Since we know that both of these routes are coming from RIP to begin with, we can tell that this loop is based on the wrong metric values and nothing to do with the administrative distance. Now, if we look at any of the other prefixes, let's say we go to switch 2 and we do a trace to those external routes that came from BB1. We end up in the same type of case, where now when the packet gets to router 6 is sending this to switch 1 instead of sending this to BB1. Where really our traffic flow to this destination should go that way, but instead it's going this way. Now again, one way we could fix this would be simply to set the metric values so that router 5 or router 6 does make the correct decision to begin with. Or likewise that switch 1 makes the correct decision to begin with. The problem with that design is that it would be very hard to predict what the metric value is supposed to be to begin with. So it's going to depend on when BB1 advertises the routes to router 6, there would be some sort of threshold where if the metric is lower than a certain number, the route is not going to loop. But if the metric is above a certain threshold, it could cause a loop. So solving the problem this way is really not that good of an idea, because sometimes it's going to work, but not 100% of the time. So we want a solution that is never going to cause a loop to begin with. And again, this is really going to be based on the filtering of the redistribution, where anything that router 4 redistributes from RIP to OSPF, 3 should never send it from OSPF back to RIP. Or likewise the other way. Anything that 3 redistributes from RIP to OSPF, 4 should not redistribute from OSPF back to RIP. And the easiest way to do this is going to be based on route tag values. So on router 3, the first thing that we're going to do is create a route map that is going to set the tag value that when we go from RIP to OSPF. So in the RIP to OSPF redistribution, I'm going to set the tag value to any arbitrary value that I want. Okay, for simplicity, I'll say 3 for router 3. That's going to be everything that is going from RIP to OSPF. On router 4, I'm going to do the same thing, but I'm going to use a different value. Okay, we'll say set tag 4. Now in the reverse direction, as I'm going from OSPF back into RIP, I want to allow all routes on router 3 with the exception of what? With the exception of the ones that router 4 already did the redistribution for. So on router 3, we're going to do a reverse logic. We're going to say route map, match the tag from OSPF to RIP. I'm going to deny any route that already has tag value 4. If there's anything else left that does not have tag value 4, I'm going to permit it. Then likewise, router 4 is going to do the same thing, but with the reverse value. Router 4 says that if the tag value is 3, it means that this is some route that router 3 already sent from RIP into OSPF. So there's no reason that I should pass it from OSPF back into RIP. I'm going to deny those routes, but then I'm going to permit everything else. So again, the route map, just like an access list or a prefix list, it does have an implicit deny. If I didn't add this second statement here that says permit 20 or permit 1,000, so anything above 10, then all of the routes would be denied. Now, under the OSPF process, when I redistribute RIP subnets, I want to use the route map that is going to set the tag as I'm going from RIP to OSPF. Then, under the RIP process, as I am redistributing OSPF back to RIP, I'm going to use the route map that is filtering out any prefixes that already have router 3's tag value. So from RIP to OSPF, we are setting the tag. From OSPF back to RIP, we are matching the tag. Router 3 is going to do the same exact thing because we have the route maps named the same values. Once we have it applied, I want to clear the routing table. Make sure that the new filter is taking effect. So clear IP route star. And now let's look at the change in the OSPF database. If I show IP OSPF database on both router 3 and 4, show IP OSPF database, notice now that the routes that router 4 has redistributed, these now have a tag value of 4. Where the single route that router 3 redistributed, this has a tag value of 3. This then means when router 3 does the redistribution of OSPF back into RIP, all of these prefixes are going to be denied with the exception of that one. Now, since this link here, the 37.0, this is already running RIP to begin with, then it's not going to be redistributed from the OSPF process back into RIP. Because on router 3, if we were to look at the show IP protocols, this link, 155.28.37, this is already running the RIP process. So it's in the database, we don't need to redistribute it back in. The end result of this should be that we no longer have the traffic loop. Now we will see for RIP, since it's going to take a long time to converge, we could either wait for the old information to age out, or we could go to the routers and flush out the routing table. So for this particular destination, for 212.18.01, the device that's making the wrong decision is router 6. Because for this particular route, we should be forwarding the traffic that way. Where currently the traffic is getting to router 6, then 6 is looping it back that direction. If we're to look at the routing table of 6 and show IP route RIP, we essentially need to flush out this bad old information. So let's say clear IP route star. And we essentially need to do this on every router in the RIP domain. One other way I could fix this would be to shut down some of the interfaces and wait for RIP to reconverge. But eventually we should see that these 212 routes, these should not be learned from switch 1. So let's try this. Let's look at switch 1 and show IP route RIP. Switch 1 is no longer installing these 212 routes, actually at all, let's say just show IP route. And we can see based on the timers in the routing table, now this is starting to age out. So with the default update timer of 30 seconds for RIP, essentially anything that goes above this timer value means that it's stale information and it's eventually going to get removed from the table. So we could wait until the flush timer expires, which is going to be 240 seconds by default, or if I just continue to clear the routing table, eventually the correct information should be reinstalled. Which it now is. We have the 212.18.00, 212.18.1, 2, and 3. These are all now being learned from BB1's next hop value. The end result, if we go to switch 2 and actually send the traffic, now it's following the correct path. If we run the ping script again, we should see that all of these particular destinations are correctly reachable. Now, if for some reason router 4 were to go down, let's say that on router 4, this link fails. This means that the RIP routes would be withdrawn, which means that the OSPF routes are then withdrawn. Eventually, this would get to router 3. Router 3 would delete its OSPF routes and then do what? It's going to delete the OSPF route with a distance of 110, but it still has the RIP route coming in with 120. So if 3 now learns the route from RIP, what should the end result be? 3 should then redistribute this route from RIP to OSPF, and router 4 is going to learn it via OSPF. So what we'll see is that the exit point that's used out of the OSPF network is going to be variable depending on who loads the process first. So right now we can see router 4 is the exit point from OSPF to RIP. If we were to go to router 4 and shut down fast Ethernet 0/1, that's where the RIP routes were being learned. If we now show IP route RIP, it means all of this information was withdrawn. If we now look at the show IP OSPF database, we see that under the type 5 external link states, now router 3 is performing the redistribution. All of these prefixes, they now have a tag value of 3. This now means that even though if the interface comes back up that we disabled, router 4 is never going to learn these routes as RIP. Well, actually, technically it will learn them as RIP. It's not going to install them in the routing table. Because now the update coming in from router 6 is a distance of 120 versus the one that came from router 3 originally, which is 110. So the only problem with this type of design is that it's still kind of non-deterministic depending or as to what exit point you're going to use between the routing domains. Since only one of them is going to do the redistribution at a time, it essentially means that whoever learns the RIP route and redistributes it into OSPF first is going to be the one that's used as the exit point. If we go to switch 2 and look at the trace route, we see now the exit point changed to router 3 as opposed to router 4. Even if we were to do this on router 4, we'd see router 4 would take the long way around to get there.